All right, welcome in. We are going to go through this example problem. It came straight out of the textbook, and it's like a physics problem. So if you've been taking physics, this will certainly be more familiar. We're going to look at it from the mathematical point of view. So we might not dive into some of the details that you're used to. We might write some things out in a different way, and we might not use some of the formulas that you might be used to if you're taking like AP physics or something. So what do we have? It says the movement of an object is the title of this question. An object is propelled vertically upward from the ground with an initial velocity of 39.2 meters per second. The distance s in meters of the object from the ground after t seconds is s equals s of t equals negative 4.9 t squared plus 39.2 t. All right, it's kind of a lot of writing right in there. What we want to focus on first is this position function right here. Okay, so we're going to use that repeatedly. We're not actually going to use this 39.2 meters per second of an initial velocity, although if you were in physics, you might be thinking about that free body diagram, right? So let's just dive in. It asks for the velocity of the object at time t. So what velocity is how the position changes over time. Okay, so the way we get that, since we're in calculus, we're dealing with change. So we want to know how the position changes over time. That's going to be our velocity, okay? And the way we get that is with the derivative. So for question A, we're just going to find the derivative of s of t. So the velocity is just the derivative s prime of t. So we're going to have velocity v of t, right? We're going to have a velocity function that finds that. So if we're just taking the derivative of negative 4.9 t squared plus 39.2 t, all you need to do is use the power rule. So we're going to bring that exponent down. That's going to give us this negative 9.8 t plus 39.2. Okay, that is our velocity at any time, right? So we just found the derivative. We found the ds dt. What is the change in the position versus the change in time? That's what that is right there. Okay, so we have the velocity, that's A. That's all we needed to do for that. And we are finished with that portion of the problem. We will then use that to do many of the other problems. So let's see. When will the object reach its maximum height? When will it reach its maximum height? Okay, so we've been given this function s of t, which is the position of it, as it relates to time. So it's important to remember that what we've actually been given when we think about this on the y-axis and x-axis is time would be our x-axis and our height is our y-axis. So our graph will look like a parabola, like this. That's not the path of the ball though, right? So if we were to look at this thing happening, like if we were to look at the ball being thrown, because it's perfectly vertical, it's propelled vertically, right? So we have that piece. So it is important to kind of differentiate what's happening there. This is going to be representing the height, how it changes over time. But this is not like a picture of the graph per se. Like the ball would be launched perfectly up. It's going to get a maximum height, and then it's going to fall straight back down, right? And then land on the ground. That's what would have like a side view of the propelling of the ball. Whereas over here, we just have, this is a graph of what the height is doing. The height is going up. You can see it goes up and then it maxes out and then it falls back down. All right. So that's going to be that's our s of t function that we were given there. All right. And that's kind of important to remember when we're thinking about this. When will the object reach its maximum height? So we do want to think about when is it going to get to this point right here, the maximum height. And so one way to do that then would be to find the tangent line. When is it horizontal? When are we going to get a horizontal tangent line? And that'll happen when the velocity is 0, right? The velocity would be the derivative of that, the change in height versus change in time, because that's change in position really. So we want to figure out for B, the maximum, when will it get to its maximum height? We want to figure out when the velocity is 0. So v of t, when is that 0? Because that represents a horizontal tangent line, right? And that would match up there. So my velocity function was, let me see, it was negative 9.8 t plus 39.2. And we're going to see when that equals 0. I want to know when that velocity was 0. And so just moving and shuffling some things around, I'm going to end up with t equals, and I'm not going to write it all out, but 39.2 divided by negative 9.8. So negative 39.2 divided by negative 9.8. And you end up with t equals, I think it's 4 seconds. Yeah, 4 seconds. You can just use your calculator for that. It's 4 seconds. So in 4 seconds, this ball that's launched perfectly vertically will get to its maximum height. All right, so I used calculus to figure that out. Like physics people, you may have another way of doing that. Maybe it's a shorthand, but hopefully this is connecting some dots for you there. And then we're going to use B to answer question C. What is the maximum height? We found out when it happens. What will it be? And so you have to know which formula to use, okay? And so that first formula right here, this one up top, we have a position function. So we want to plug into the position function because that tells me the height at any time, right? That tells me the height, the distance s from the ground. So if I plug in different times there, that'll tell me how far away from the ground I am, right? If I plug in 0, by the way, I just get 0 because I haven't launched it yet. So if I plug in 1, it'll tell me how far off the ground I am after 1 second. I want to plug in 4 seconds because that'll tell me what the height is at its maximum, right? So for C, I want to plug in S, it's S of 4. So I'm just plugging into my original position function 4 seconds. And so that would be negative 4.9 times 4 squared. And I'm just pulling this from the above problem there, plus 39.2 times 4. And I just plugged all of that in the calculator already. Clicking away, clicking away, clicking away. And you get 78.4 meters, 78.4 meters. So that's how far off the ground you are after 4 seconds. In the next video, I'll probably just work on finishing this problem since it's already been about 8 minutes, a little bit less than that. So I will work on questions D, E, F, and G in the next video. Thanks for watching.